So I'm going to resume slowly so that eventually others can join. Are you having a look at my slides? I don't think so, right? Okay, so let's okay. So while I let the others address, so in order to resume, I'm going for I'm zooming in and zooming in into data, and hopefully at the end of the session we will start having a look at some solution to prepare eventually the hands-on session, so that you can also touch a little bit what I've said. So, but let's move on with respect to data, so that we wrap up the theory about the. It's rather. I mean, what I want to make sure is that you acquire the right vocabulary of both big data, data science, and that you understand the link between both, and then in order to be able to go through the design of experiments and having a more practical point of view of all of these concepts. So if we continue zooming in into data, as I said almost at the end of the previous session, there is a general definition of big data. It is important to have in mind this, even if, as I said in the previous session, this has to be calibrated with respect to today's vision, because we are having access to a lot of resources, almost on an unlimited way. So reaching the edges of existing solutions is quite difficult, despite the fact that we could be dealing with data, big data, so-called big data collections. So the general definition of a big data collection is that these are data collections with characteristics difficult to process on single machines and traditional databases. This is the part that is still on the line. Okay, so despite the different properties and the different degrees in which a data collection can be characterized with respect to the 5B properties that I have described previously, the idea is that these are collections for which you need much more than one machine, and that traditional databases are kind of limited, and that you go into new techniques that can address the problems implied by the properties I have described previously. And so, which comes to the second part of the definition, it is a new generation of tools, methods, and technologies are there to collect, process, and analyze massive data collections. And this is the status quo. Okay, we have indeed new generations of tools, methods, and technologies that allow us to collect data continuously under different conditions. We can process them and we can analyze, despite not only their volume, but the different properties that I have described previously. And these characteristics imply that even if transparently or not, we have to revisit the way we use computing and we develop computing solutions. So we are moving from the traditional sequential way of addressing, of writing programs, and we have to move towards parallel processing. And of course, and that's because of the volume. We have to go through distributed storage solutions. That's something that will be there for now, and I think that forever. And so this is the context in which we are now with respect to big data. Okay. Now, as I said, what is really important is to understand the V's, so the characteristics. And but what is very important is to understand which is the real value of data, okay? And then here, as you can see, there is no value in the properties, but this is a guiding element you will see particularly when we design experiments, the value, the implications, both in economic and non-economical criteria that determine the conditions in which we process the data. Now, that's also for your culture, for your general culture. The properties that I have described, the 5 of them, belong to the so-called V model. Okay, so as an anecdotal way of describing the properties of data, people started to define properties starting with V, and they defined this V model. At the very beginning of the trend, there was a 3V model, which volume, velocity, and variety. And then other models started to come up, and then other properties that I haven't discussed appeared. For example, in the 4V model, there were variability, which referred to inconsistencies by constant meaning changes. Okay, so since because of variety, and because of data coming from different contexts, people tend to evolve, okay, about the way they describe observations and collect their data, and this variability is part of the property of big data collections. Then there was veracity that we discussed, then the 5V model and so forth went to the value, and then there are 10V models, etc., with many different V's that in fact address aspects of big data in specific disciplines, okay, essentially. So, a most reference is the one of Mike 2.0 in 2012, where this big data description had started, but we have a later on Jagadish with the V models, and he discusses these properties. So this is one of the, we will do a practical exercise, but in order not to forget, and if you're interested in formally reading about the V's, this paper of Jagadish is a seminal one. So this is important. Of course, there is a reduction of the way the sizes related to volume are defined. You remember that normally is 2 a la something, 2 to the power of something, the way we measure the size of the data in computing science, but as an abuse of language, and in order to democratize the sizes to non-specialists. So these are some references. I was talking about terabytes, which is this number of bytes. Remember that of course you have the bit, but then the bytes is the size of some words, the representation of some minimal representation of data in some computers, and then you can go further. So petabytes, exabytes, zettabytes, and jottabytes. So when I was talking about the brontobytes, is 1,000 this size of information. Okay, and 1,000 times this size is G of byte. As I said, this initiative to start rethinking the units, and with that rethinking the capacity of computing resources, is part of an initiative driven by IEEE. Now, some years ago, it was during the while Obama was in office, and so they started to discuss about this in this seminal reference, and particularly because they started to define very ambitious data-driven problems and projects that were the killer applications that suggested and argued in favor of dealing with such quantities of data. And one of the major reference killer applications was the project about the brain, which was then, the European Union adhered to this project, and the idea is to digitalize the processes happening in the brain in order to study them from many different perspectives, neurosciences, of course. And so this was the kind of projects that drove this initiative and that make it possible to be in the status quo today with really huge capacity of storage, of processing, democratization of huge experiments, and data-driven applications. And so this was the slogan of the initiative. We are not going to dealing with big data will be normal, and we will have to deal with hell of a lot of data. Now, beyond the size and the properties, in fact, what happens is that data collections have a life cycle. They are not immutant elements. And in every step of their life cycle, there are different strategies, different methodologies, and different technology that can be used in order to make this living element go through time and then be available and usable. Of course, the life cycle starts with harvesting. How do we harvest the data? And there, this touches the kind of hardware technology, which means sensors, which means applications with software sensors that report about the way they work, explicit production of data, like the one we do, for example, when we use social networks. And so these harvesting strategies are the first thing to be done in order to start a big data collection cycle. Then, as we have said, technology is not perfect, and conditions always have variability, etc. And so the data do not come clean and pure and ready to be used. There are some problems. And so part of the initial phase of the life cycle is cleaning the data. And cleaning the data has a lot of implications. There you call to mathematical models, to linear algebra strategies. So many models that we learn particularly in our university education, that are applied in order to clean all this data, and of course in a timely manner, because some of them are used to solve critical problems. Once you do this, even before cleaning, you need a way to preserve the data. Question is, are we going to preserve all the data that we collect? For example, take the social network. One of my favorite ones is Facebook. So all the stupid things that we produce producing on Facebook, and all the interesting things that we produce on Facebook are there. You can, if you are developers, you have a developer account, you can access the data that you have produced from the beginning of the subscription to that social network. And it's huge. And well, the bet that this company has done is that they maintain the data, even beyond the fact that some users have passed away, and there is a way of transferring grant to the use of the data to other persons, and then maintain this data. So, but for how long and what for? Okay, so there is an important decision-making problem on how long and which data are we going to preserve. And depending on the period of time in which we want to preserve them, and the way, whether it is explicit or compressed, etc., that we want to preserve the data, there are different solutions that we can use. There are those that deal with cold data, and there are others that deal with hot data, which is the data that we are really going to use in order to solve problems, etc., immediately, or more or less immediately. So there comes as a traversal solution all the technology of data management and stores. How are we going to, which storage solution are we going to use in order to be able to select, query, etc., the data? And so this is a problem that refers to preservation. Then once you preserve it, at some point you want to answer a question, and you are looking for selecting some of samples of data that will help you answer your questions. No, and so you are going to process and analyze this data, and from many different perspectives. Now, in a minute, I will tell you that it's not only it's not all about discovering, about analyzing. There are many questions that we have about the phenomena that we observe that can be solved with classic solutions or with aggregative solutions that do not need rocket science in order to be answered. And the challenge for you as professionals is to determine to which extent your questions are answered with classic solutions, and to which extent others need some specific, more particular solutions. But anyway, processing and analysis is an important phase. And this is an important phase also because new data is produced as a result of these processes, and these data feed the initial collection. Okay, so every time you go through this life cycle, you might be feeding the initial data collection with new data. Okay, and it is in this way that it is a moving and a living element and not a static one. Okay. And then once you have processed and analyzed the data, you are going to exploit the results of this analysis, which will produce, again, more data that will be harvested, cleaned, and so on and so forth, and here forever, or until an event or some decision comes that stops the process. Okay. So this is now we have seen the static perspective of the data, and now, in fact, this is happening consistently while we develop experiments and do whatever we want with the data. And this has to be controlled. This requires decision-making and solutions, IT solutions in general, that must be considered in an organization in order to get to be able to drive solutions through data. Now, I want to make a kind of disclaimer on what you have probably learned. So I'm assuming that because you have done engineering and because you certainly have had computing science courses, and because eventually a part of the basic knowledge that is supposed to have an engineer is related to data management and to the relational model. I'm going to assume that you are more or less acquainted with this knowledge, but if you are not, do not worry, I will not go further in very complex elements and notions, so you will still be on the same page with those that have addressed the problem. When we, at the beginning of the history, when the problem in companies was dealing with the employees and the departments and the salaries, producing the payment monthly, there was a milestone in data management, which was the definition of a model, a mathematical model based on the notion of mathematical relation, that intended to have a representation of the data, of consistent data collections, and then a set of operators that help to query the data. And the principle was that the database contained facts. It was a snapshot, a consistent snapshot of a mini world, of a company or a department, etc., an organization. And it was possible to ask questions, factual questions, on top of the database. And these questions, the response were complete and sound with respect to what was contained in the database, with specific guarantees that made it possible to support this hypothesis. It's a very controlled work. In this perspective, the big problem was building the database, right? So it was more or less the problem that I have described. Data were harvested from different departments, etc. There were people injecting data about employees, about their activities, etc., and at some point about the activity of the departments. And then this was loaded in a database, and in order to do that, the database had to be designed. And the principle of this design was that the person who designed the database had to understand the way an organization functions. Okay, so if it was a department, let's say a retail organization, well, it was organized into departments. The departments had a head, had certain number of employees. Then the employees were represented by their name, their social security, they had a salary, etc. So the way the organization worked was represented as a set of data structures that would then be fed with actual data. Okay. So in terms of data, what we did is we modeled a mini world. Okay, so the retail organization, a hospital, a school, a university, whatever. So this was the mini world, and we represented the entities that composed this mini world, and we fed this with facts. And once we have this, it was possible, as I said, to query, and the queries were precise. They used the terms that refer to the database, and there were specific operators that we could apply to the data stored in the database. Okay, and more than that, there were also associated constraints. that were respected when we managed the database and when we queried. Okay. This is not only relational solutions, but this is also how the search engine works. You have the search engine, it doesn't represent a mini world, but it harvests data, which are text and textual data from the web, and then the queries are specific. There are terms, keywords, and the keywords can be combined according to specific operators. In the case of the search engine, these are conjunction, disjunction, and negation if the search engine is very evolved, that represent the question. It's a factual question, and the answer is a set of data, that of text, of pages that are close to the specification of the query. Also, this is, but anyway, this is the principle of this kind of solution. And so the results are collections of items. They can be complete in the case of the relational models, or partial, as in the case of search engines, and they correspond to consumers' expectations. And when they are not precise, as I say, and when they are partial, there are scores that determine to which extent these partial results correspond to an answer to the question. Okay, so that's something that is there and that many organizations use. And then you can have several databases, not just one, and they can be combined, and still you can query and answer factual questions. Now, when we move to this stratification spirit and analytics, etc., we are completely changing the philosophy of managing and querying the data. Okay. The problem is that both of them coexist in organizations. Okay. And so since both of them exist, we have, as I said, to figure out when we are addressing this classic principle and when we are addressing the analytics principle that I'm going to describe in a second. Okay, so this is the challenge of you as experts in different disciplines that want to exploit the data in order to solve problems. Okay. Now, let's see an example of the classic situation. Imagine that we have a hospital and a general medical system where people deal with people contracting diabetes. Okay, so you can have, if you want to describe this kind of mini world, you can, for example, consider that people go to clinics, and clinics are organized into departments, and each department has an encounter, and this encounter produces a diagnosis. And in order to produce this diagnosis, the encounter uses vital signs in order to determine the diagnosis. And the encounters have providers that will help them deal with these vital signs and then produce diagnosis. And then these encounters deal also with lab orders, with medication orders, with lab results, and they have specific procedures in order to deal with all these problems. And the encounters have associated patients, and the patients also have specific data related to the services they have address, because they have to pay the services, or they have to have an insurance in order the services to be paid. And these clinics can be, for example, accessible through applications, so that you can go to specific clinics when you have to deal with, when you want to deal with your disease. And so, given these examples of questions that can be answered are, for example, average of lab and medication orders per client and physician in a given clinic. Okay, with this classic factual set of data, it is possible to answer this question. We can also ask vital signs and lab results used to emit a diagnosis for a given patient. Again, even if there are a lot of vital signs and results coming from different labs, etc., at the end of the day, it is possible to, given a diagnosis, to track where the data come from and understand which were the elements that led to a specific diagnosis for a given patient. Then we could also ask the number of patients with diabetes followed per clinic. So these are classic factual questions that we can ask in this classic approach. For a long time, and this is why maybe you as non-computing science experts have to study this, because normally these kind of data are available in organizations, and if you either you express your requirements to someone, or you can and this someone will implement these requirements such that you can have applications that answer them. And if you want to move, to acquire data science expertise, and then have a kind of hybrid experience and expertise in order to deal with data-driven solutions, then normally you have to be acquainted with the way these queries are expressed in specific languages. Yet I want to point out that this expertise is today moving a little bit, because new solutions are emerging that are abolishing the need of non-computing science experts to have a deep knowledge of solutions that tend to be technical and very proper of the type of management solutions that have been developed in computing science. And I want to use the way I choose ChatGPT in order to remind you about the relational operations in a language called SQL that deal with this kind of factual questions. If you are not acquainted with the relational model, you can see that in some years, maybe this will not be dramatic, because there will be solutions ready to use, prêt à l'emploi, to address this. But for the time being, it would be important that you go through, as a complementary knowledge of what we are going to deal with here, to make sure that you have a fundamental knowledge of this type of querying, because, as I said, it is important to determine when to use this solution rather than a more discovery-oriented solution. So I'm going to switch to ChatGPT a moment. And I wanted to show you this. I think, yes, you are watching. You do watch my browser, right? So for those that are not acquainted with this ChatGPT story, if you are users as an alternative for searching for information, You have the option of using a chat environment, and with this chat environment that relies on artificial intelligence models for searching information and deducing information, it is possible to deal with some questions. So let's have a look at to my question. I asked it to consider a relational schema, so the kind that I have described for the hospitals, but I choose to have a simpler one so that I could explain in a simplified manner. So I asked it that there is a well-known schema about employees and departments, and I even wrote with mistakes. I'm asking it to write SQL examples with the 5 operators that are associated to relational algebra. So if you do not remember, once you have the relational representation of data, there are 5 basic operators that define an algebra. And so there is a relational algebra that is the basis of the of querying a relational database and then optimizing, etc. Okay? So when we talk about relations, remember that from the mathematical point of view, a relation is a set that comes from the Cartesian product of a set of domains, and the elements of this Cartesian product are called attributes. Okay, so we combine different attributes that are associated to a domain, integer, string, etc. And these Cartesian products of these different attributes compose a relation, which is itself a set, because the result of a Cartesian product is a set, which these elements in its set that are called tuples. Okay, so it is possible to represent all the elements, for example, the one that I used for the hospital, as relations, and then which represent sets of data. So we have employees and departments, and it provides and it gives us examples with the 5 operators, basic operators that can be associated to a relational database. Okay, so there is selection. Okay, there is a projection, and every time it provides us with the expression in SQL. So, for example, in selection is give me the employees that earn a salary higher than $50K something dollars, let's say. Then we can ask for the department where employees work, okay, with the name of the employee, the department where he or she works out of the relation employees. We can perform the union in order to combine tuples from the 2 relations and then produce a new relation. For example, unite the names of the employees of the relation employees, and then with the names of the employees working in specific departments. Then we have the difference, and we have the Cartesian product. So these are the 5 basic relational operators that can be applied to a relational database and their expression in SQL. Okay, so the question comes whether us as users of data analytics and data management solutions, we really need to master SQL, or rather master the expression, the statement of the problems. Okay. Until now, at this very moment, what I would say is that we have to master the statement of problems. We have, as non-computing science experts, be able to formally state problems and then leave the development of solutions to IT experts or to computing science experts, and be able, when they provide us with the results, be able to determine whether the results correspond to our expectations. Maybe critically it is more difficult, but this shows that we can delegate technical aspects to the experts of the domain and really concentrate on the problems of our disciplines. Okay, so that's but that's my very opinion at this moment of history. I don't know if while other things will come up, I will change my mind and say that all people, even non-experts, should be able to master SQL. Anyway, the thing is that facts, aggregations, and problems that do not go beyond what is represented by data can be solved with classic solutions, existing solutions, okay? As long as we state our questions formally and clearly. Now, when we move to data science, we are completely changing the perspective. First of all, data. The type of data I have described in previous minutes with these V properties, in fact, do not represent a mini world. They represent observations of phenomena or of subjects of study. Okay, so this is a huge change because the person or the community that wants to observe the phenomenon declares with respect to their expertise that this phenomenon can be described by a set of variables. Okay, if the phenomenon I'm observing is a person, I can say that his or her weight, age, race, temperature, heart beating, etc. These variables represent its his or her physical status. Okay, but where does this come from? From the expertise of physicians and experts of the human body that declare that this set of variables can model the physiology of a human being. Okay, and so there is no database design process. It is something declared by this expertise, and the data that are collected include these values related to these variables for representing the status, for example, of a human body at a specific instant in time. Okay, so completely different. It's not the same attributes as the attributes that I refer to. These are features that represent, for example, the status of a human body. Physiology of a human body, or the status of traffic, or the status of sales, okay, the evolution of the market, etc. So first main difference, we deal with observations. Second main difference, the purpose of queries in this context is analytical. We want to have insights or foresights about the phenomenon. Okay, so the line that I described with the different types of questions that we can ask: what did it happen? Why did it happen? Can I predict how does it happen? And can I reproduce the phenomenon? These type of questions are analytical questions. And they cannot be expressed and implemented in one shot. It's not like my ChatGPT example where I have a line or 2 lines expressing the question. Path, nothing more. Here, I need pipelines of operations that step by step will allow me to produce some elements that will help me to analyze the phenomena. And this set of steps must be guided by a certain number of conditions and characteristics of the data. I have to know, beyond the fact that the data are observations, some conditions in which these observations happen are valid or are problematic. And out of this, I will develop this set of steps in order to analyze the phenomenon, partially, of course, because no, I have shots of the status out of these observations, and then produce some results. And then, completely different out of the previous principle, results are not the data. The results in this context are models, are functions, okay? And these functions represent the understanding of a phenomenon, okay? Which is the function that best represents the way the values of physiological observations and status, the values that deal with the fact that a person contracts or not diabetes. So these models are not definitive because we do not have the complete set of elements of our observations, and the observations are done within intervals of time. They are associated to assessment indexes. They are not definitive, and normally they have a margin of error. And all these scores are associated to the result, to the model. And normally the results, the good result, the one that we retain as valid result, is accepted by comparison. In fact, we are going to run different experiments using some variables, using some strategies, etc., within our pipeline, and then scoring the results, and the result that gives the best scores, numerical and also with respect to the experts, the domain experts, we consider that this is a result, okay? It's not final, but it's an acceptable result, and we can survive for a time while new data come, and then we see whether this hypothesis is true or not, okay? Now, how does the pipeline looks like? Well, as I said, it's no longer a 2 or 3 lines SQL expression. In fact, what happens is that we are going to start with raw data. Maybe different collections or just one collection. And the first thing that the pipeline must do is a set of tasks that will help a person explore the data in order to understand its content and its characteristics and its quality, and then eventually prepare the data so that it can be useful in order to answer a specific question. One question, one pipeline, okay? We cannot answer several questions with the same pipeline. That's not possible. Now, normally, when we explore and prepare the data, in fact, this is a numerical, or it's a mathematical these are a mathematical set of tasks normally quite associated with statistics. So in fact, exploring and preparing the data means providing a quantitative understanding of the data. And therefore, we rely also on visualization techniques and plots that help someone understand all these characteristics of the data, which means that all these, in classic solutions, there is no human in the loop. You rely that your SQL expression is correct, and then it is executed, and that's it. Whereas here, all the process is guided also by a human. A human will go and see the results and make decisions on how do we move forward into the different steps that will lead to a data set which is explored, understood, and prepared in order to answer a question. So that's an important thing. Another important thing is that all the partial results that are produced here belong to the life cycle of the data collection and must be gathered and stored and smartly associated to the initial data collection. So that set of different tasks are the first part of a pipeline. And they are, well, this is called data exploration and preparation with its element of visualization. Once we have done this, in fact, what we produce is a data set prepared for answering the question that drives this whole pipeline, okay? The second part of the pipeline refers to which are the mathematical or machine learning or artificial intelligence models that I am going to apply in order to analyze this data set and produce some model with its assessment. The kind of models that algorithms, if you want, that I will use depend on the family of questions that I'm addressing in my research question. Is that I'm looking for insight or hindsight? Am I looking for insight, or am I looking for foresight? So that's the first thing. The second thing is that depending on the quality I manage to produce associated to the data set, I will determine whether I am going to apply powerful but very strict mathematical models, or whether I am going to prone for other heuristics coming from machine learning or artificial intelligence in order to solve my problem, or whether I am going to combine all of them, okay? For every model, either mathematical, machine learning, or general artificial intelligence, there are rules about the way, the format, and the form of particularly the mathematical characteristics of the data set that I will use to feed them, okay? Some of them can deal with the whole collection, and other models need training, okay, need to deal with a sample of data that is used to train them. And once they are trained, they are validated with the rest of the data, okay? So which are the good ways of choosing which will be the samples that I will use to prepare to train the model, or to have to train the model, and which I will leave in order to test it. This is a huge decision-making, mathematical decision-making problem that is included in this sample fragmentation of the data. Then, depending on the tools, algorithmic tools that I will choose, I will perform and do a lot of back and forths, because all these models have parameters, okay? They must be calibrated. And calibration is a huge problem. And so I have to determine given a sample or all the data set, which are the right parameters for a model to produce good results, or results that can be considered to be compared with other results in order to determine whether they are solutions or not. Okay, so these are these two processes that are included in this analytics phase, with the error analysis and ablative analysis, which are used in order to assess the results. So this is a recurrent process that happens until I converge. And where do I converge? When I have numerical results, reasonable numerical results, and when a domain expert validates them. Okay, and here again, there is a lot of human in the loop, both from the algorithmic side, from the data engineering side and data science side, and also from the expertise side. Okay, and so all these people work together in order to perform this set of tasks until they decide that they have converged and that or not, and that they are moving forward to address other problems or to have more data in order to make sure that all these conclusions are valid. Okay, so completely different perspective and completely different challenge and complexity. Okay, so the idea is that all this is an experiment, and in this course we will have a first touch of different elements to let you feel how does this process happen, and that eventually you can use in your practice. I am going to check because I forget, but I don't have questions. Do you have questions until now? Or you are perplexed about all this bunch of information coming today? Don't worry, we will have hands-on, and I will be moving back and forth to alert you about the relation with this conceptual part and the practical part. So if there are no questions, yes, I do have one. Which part takes most of the time? The data, the first part. Sorry, this part takes a lot of time because here you have the problems of variety, volume, veracity, and so you have to deal with this here. And deciding which is the right way of, first of all, of understanding, and then of preparing, it takes quite a bunch of time. Here, there are, particularly today, strategies to automatize the calibration, for example. So the burden is quite reduced because it can be semi-automatized, and the human in the loop implies, going through the results and the scores, but not really calibrated by hand the models, etc. So that's why this takes a lot of time. And thank you for the question, because there are, for example, emerging startups. They are more or less consolidated today, but there are still emerging startups just providing solutions to ease this part, because it's a huge problem. And then, well, not today, but eventually you will see, however, what does ChatGPT does with this part, particularly this part. Not these parts, but this. So anyway, it costs. More questions? Okay, so example. The pipeline that I'm referring to here is defined here. It's a complex and repetitive processing, a set of processing and analysis tasks. Okay, how much, how complex, etc. This depends on the problem. And so, for the time being, these pipelines are done in an artisanal manner. Okay, so there have started to emerge some dedicated languages, programming languages that can ease the process, but they remain, there is, as I said, it's one question for one pipeline for a given question and for a given set of data. If you change the set of data or you adjust a little bit the content, the context of the question, not the question, but the context of the question, you have to develop a new pipeline. And this is why also there is a huge market for data scientists now, because for every problem you need their expertise in order to figure out how to design these pipelines, and then data engineers in order to put them on the run, and they can be used in real applications and maintained. I am coming back to trying to show you how this can be seen in a concrete example. So consider that we have a labeled set of data, of observations, where we have a set of physiological values, weight, glucose level, etc. And whether given this, the person has diabetes or not. We have these observations. And now we want, using this data set, could be here, we want to predict diabetes, giving these specific variables. Well, what the pipeline that we would have to perform in a very simplified manner would be the following. First of all, as I said, we would have to understand the data, and therefore we would have to explore them and eventually prepare them. Today, there exist different libraries and languages that allow us to perform this in quite comfortable ways, particularly if the data are tabular. So imagine that we have these observations with variables, physiological variables, and then an attribute diabetes, non-diabetic, and etc. like that. So what we could use, here the example is with Python, but I believe that you might be R users or other tools users, so with the tool that you prefer. The first thing that we would have to do is understand the content of the data set, and what does it mean to understand it. First of all, of course, we would have to see whether there are outliers, null values, absence of null values, or to which extent we have null values, and non-determined values and outliers in order to determine whether which is the content of the data set. And another thing that it's important is to see the balance, okay? In order to predict, I would need to have a representative set of cases where the person contracted diabetes with respect to the set of observations of people that didn't contracted diabetes. Because if the data set is unbalanced, I might have diabetes. I think that I'm having connection problems, but I'm going to persist. Just tell me if at some point you listen or not. And it's still recording, that's important. Okay, so this data exploration part would do this with some libraries, but particularly using descriptive statistics, okay? Then a person would choose which would be the right way of performing prediction. And she or he would decide which is the good model in order to predict. For example, let's say that the person decides that since either I have diabetes or not, logistic regression would be a good way of predicting diabetes. If such is the case, then this means that I have to train the model, right? Which means that I have to determine which is the training sample that I will use in order, from the initial data, in order to train the model. Then I will train the model with this training set, and then I would test the model with the remaining set and determine compute scores in order to determine whether it predicts, to which extent it is able to predict diabetes cases, okay? And so much and so forth until I define. So which are the important elements to consider? Well, here, for example, if my data set is not balanced, what do I do? Do I generate synthetic data? This is a practice in data science. Or whether I balance my data set with the representative number of non-diabetic, for example, with respect to the diabetic, in order to have a balance, and then I need to justify how do I select this, or whether I decide not to use logistic regression because of this problem, and then decide other strategy in order to predict or expect to predict, for example. Then the fragmentation aspect is also important. How am I going to select the right representative observations that will ensure that the model is correctly trained? Okay, so that's another important thing. And then, of course, the assessment scores, because here, again, I insist a lot, I would need a health expert or a physician in order to determine whether my solution is a good solution and a useful solution or not. So this is an example of how would a very simplified data science pipeline would look like with respect to this complex thing that I showed you here. But you can identify the elements that I said. You have observations of the data. The results is a model, is a prediction model, and it has assessment scores, and the objective is analytical, because I would like to predict diabetes out of observations of the field. Now, before we move forward into more details about this data science experiments design, which is the next aspect that we will consider, particularly once we will start the hands-on, is it's not only about the conditions in which data arrives. Okay, so it should be of good quality, etc. But it's also a matter of how the data is going to be consumed. Okay, so when we are the ones consuming the data, we have to figure out how is this data how does it arrive to us? Okay. For example, it can arrive in different sizes. If I'm testing and seeing whether how would I address a prediction problem, for example, for diabetes or other things, I have to determine which is the data that I'm going to use and how big is it with respect to the context in which I am going to have a test on the design of my pipeline. Is it possible to have access to different sizes, or do I really have to receive the bunch and then it's up to me to prepare some representative sample that I can use to test my design? For example, if you consider Stack Overflow, Stack Overflow is a social network that you probably know. It's for interacting with experts of different levels, in programming experts, to address computing problems. Okay, so they export the interactions in order to determine, for example, expertise on parallel programming or on Python or on whatever. And so they export data sets of different sizes, such that if you want to just test, you can have a small data set and then test in a normal computer with few resources requirements, for example. So this is, or Wikipedia, for example, does the same thing. Then it is important to know the quality of the data. We have already discussed it, the uncertainty and the ambiguity degree. Okay, this comes to the conditions in which data are harvested. Okay, I would like to know which are the type of sensors, for example, used in order to collect the data. If I have commercial sensors, of course, the reliability of the observations is less good than if I have professional sensors sensing, for example, a body. No. Then I have to know also whether the data which is produced evolves in its structure, in its completeness, and in the way it is retrieved. Okay. Then all the context that surrounds the way the data are collected is very important. Today, more than ever, we are talking about giving back control to the owners of the data, their data collections, okay? So did they accept it really to be observed or not? And whether we can use these to perform experiments. And access policies, okay? So this comes data, I mean, in a very general way, we use them and we assume that we have the right to do that, but in fact, this is related to data governance, and there are rules in order to use it and to exploit it to perform experiments. And then the other aspect is when we perform experiments, this is in experimental sciences, is very, I mean, it's natural. Experiments must be reproducible. Otherwise, I mean, you conclude things, but nobody can verify the way you set your experiment, their validity, etc. So you have to design the whole data science pipeline such that it can be reproducible, okay? And that while you are particularly preparing the data, you are, or modeling the data, you are not producing software artifacts. What are software artifacts? I am going to give you an example. I used to work with a neuroscientist working on pain. And the idea was to figure out which are the cells in the spine that produce pain, because sometimes pain is not there, but people still feel pain, okay? And so they want to determine why do these cells continue to be activated to feel pain, even if there is no real pain in a body, okay? And so they were very worried about the fact that when you prepare the data, I mean, you can imagine, because you know mathematics. I mean, if you are performing, for example, to impute absence of data, you can perform how do you call it? Estimations of possible data out of the existing data, no? And you can adjust the values, and maybe if you are using a discrete model, you discretize things. But when you are doing this in cells, you might be modifying the representation and the signal of the cell, which means that you might produce a drug that controls the pain and that it's not effective because you imputed maybe a signal from a cell that you considered anomalous and that it was not anomalous. Okay, so this has important implications. Data preparation is, of course, a numerical exercise, but every time you move and you tune the numbers, you might be tuning the observation, the corresponding situation in reality. And this has to be avoided. And this is why you have to work with experts. So all this has to be done, and I come back to the properties, with considering the properties, okay? I'm telling you that, for example, you can do extrapolation, for example, for engineering or preparing the data. What happens if there is a lot of variety? I'm having a sound, and I don't know if it comes from you or from me. I think it comes from you. So again, the same with the volume. The same as in my example of the temperature readings, am I going to impute anomalous readings where the thing is that they are not anomalous, but that they are just they correspond to the result that is close to the window and not otherwise. Just give me a second because my headphones are running out of battery, and I'm going to move to the to here. So all these elements, as I said, have to be calibrated with respect to the properties of the data that we have discussed. And of course, value is always there. I will tell you why in some minutes. I hope that I'll have time to do that. So I'm not going to use this because I have already told you this. Just to tell you that when I presented the data science pipeline, I said all the intermediate results that come out from the different tasks that are performed throughout the pipeline must be gathered. This gathering of tracks of the experiment is called data curation. Okay, so there should be someone helping you to curate the data that you use and produce in your experiments. Why? Because they need to be reproducible, and you need to have explanatory decision-making procedures, okay? So since you need evidence to say that you decided to, I don't know, to declare that someone has diabetes or not, then all these data have to be there, have to be maintained, and have to be accessible in such a way that when you produce the final result of your pipeline, the result is argued and complemented with all this evidence. So data curation is an underlying and horizontal process that should be performed in the back end of your experiment. And of course, this is not up to you to do it. This would be the infrastructure that you use in order to run your experiment that must provide you with the service that allows to curate all this process and then give access to it to you and to others that would like to reproduce and understand the experiment. Now we are reaching to a kind of short practice, but before this, well, I have talked about data. I have talked about properties. I have talked about classic solutions like relational one. I showed you how this now is moving to a very mechanical thing that can be done by solutions as ChatGPT. And I have shown the complexity of all the elements that have to be considered to design data science pipeline. And throughout all of these, you have solutions associated to data. And the important thing is to be able to classify them such that you can, as I said, make decisions on who is who. Okay. So it is possible to draw a data spectrum and see which is the position of the existing solutions with respect to data processing, querying, analysis, etc. The first thing to consider is that data are not just data. Data collections are determined by their degree of rawness, the rawness of the data. Okay. So you can have really raw data just coming from signals. And you can have on the other side of the spectrum very curated data, even lying in servers already designed, for example, in the relational model or equivalent, already lying in an organization. Okay, so you could try to answer analytical queries on top of deployment and department and employees. Okay, so very curated, and still you can try to answer other questions that go beyond the capacities of SQL. Okay, and this data is quite curated. They have restrictions. They are not nuls, so they're really, really curated. And still you could do that. Or you could do this in data lying in a search engine. You remember that data lying on the search engine, the representation is a statistical one. Okay, so for every term in the text, we have frequencies, or we have the probabilities of a term to appear in a specific document, right? So this statistical representation is quite curated, and you still could perform analytical processing on top of it. If you don't, you still have operators, factual operators, like aggregations, like all the sets operations, union, Cartesian product, difference, case, which are, we know the semantics, the operational semantics of these operators, or in information retrieval, we know how the search engine works, and we can determine which are the conditions in which our results are produced by our favorite search engine. So this is what is possible to do on top of curated, very curated data. This means that I cannot perform a relational or aggregational queries, or even queries as the ones we perform in information retrieval on top of data with highly raw. This is not possible. They have to be curated, and once they are curated, organized, clean, blah, blah, then I can perform this. Okay. Whereas I can apply other strategies on top of curated data. Okay? So that's an important thing to consider. Now, when I go back to this raw data, which can look like this, or like this, or like this, The very first thing that I can do with, particularly with data with high degree of rawness, is data exploration. Data exploration includes, as I said, performing a quantitative profile of the data. We are talking about distributions of values. We are talking about frequencies of values. We are talking about percentage of null values or of absent values. We are talking about possible outliers, okay? So all this kind of exploration can be done here, okay, with highly raw data. While we move into less rawness, we can start, for example, performing hindsight of the data. As I said, computing indices of descriptive statistics implies having a cleaned data set in order for them to be representative. Otherwise, it's, I mean, of course, we produce values, but these are not representative values, okay? So here, we suppose that we have less raw sets of data, and then we can start performing hindsight, performing insight, for example, or prediction when the data have been more organized, cleaned, and where the mathematical properties of the values respect a certain set of constraints, okay? So all this here is implemented by, as I said, mathematical models or heuristics if we are using machine learning or other types of artificial intelligence methods, okay? They can resist more or less high degree of rawness. Particularly, for example, if you're acquainted with deep learning, which is very popular today, it can resist to this, okay? Whereas other strategies like classification, for example, you need somehow to be here, okay? So this is the spectrum, and the objective here is, as I said, to have some hints on the different strategies so that you can go to your practice and apply them. Now, we are moving towards a little bit of practice, but before this, well, I've been talking about a lot of resources and having access to GPUs, and yes, and who is going to provide us with all of this, okay? Well, in fact, with respect to computing resources, in the last 15 years, there has been an evolution on the way we consume them, okay? The way we consume computing resources. And a very practical solution is has come up with the appearance of the cloud. Okay. The cloud, first of all, is an architecture. It's a computing architecture. It provides computing resources, accompanied with other services such that we do not go to the disk and manage pages or objects, right? So that we have a kind of transparency layers in the hardware in order to ease our lives, okay? But in the very sense, it's a computing architecture, which is very interesting because it has the promise that it will provide us with the right amount of computing resources, and that if we need more, it will provide them in an unlimited manner. Okay, if I need more CPU, more storage, etc., the cloud is able to assign to me this kind of resources. Okay, with a particular constraint, and here comes value, economic value, under the condition that my credit card has enough resources so that I can pay for what I am consuming, okay? So it's the provision, the way it works is, it is possible to access to computing resources and software resources in a flexible and possibly unlimited form under the economic model called pay-as-you-go model. Now, the cloud has a reference architecture. And this provision of resources makes it possible to consider that anyone with accessing the cloud will be able to store big data collections and run greedy processing, because she or he will access to the necessary resources, okay? Now, the cloud has a reference architecture, and the reference architecture is a layered one, okay? So you can, and in the unit of access to the cloud is called a service. We are going to access to services provided by the cloud. And the services belong to one of the three general layers. At the very lower part of the cloud, we have hardware services, and they are called infrastructure as a service. So I can access to CPU or computing cycles of different hardware. I can access to main memory of different types, and I can access to storage, to disk of different characteristics, technological characteristics, okay? So this is the lower layer of the cloud, which means that if I'm running an experiment, like the one I have been describing, and I say, well, I need, there is a lot of visualization, and I need very good rendering in visualization because I'm dealing with continuous data. So I need GPUs, or I need, my algorithms are very greedy and I need them to run fast. So GPUs will be a good way of addressing my problem. So please, cloud, provide me with X number of GPUs of these characteristics, and you have it, okay? Now, as I said, no one in, you need a transparency level where you do not directly touch the hardware, and this is called platform as a service. For example, you can decide in a specific environment the type of operating system that you want to work with. You can decide which type of file system you would need, whether you want it to be distributed or not. So this kind of services, which are horizontal services that allow you to manage and to coordinate the access to the infrastructure, are called platform as a service. And then at the very end, you can have already ready to use pieces of software that you are going to compose in order to build your applications. And this is called software as a service. The cloud can be accessed horizontally, so you can only have access, decide to have access to infrastructure or to platform, or you can cut in a vertical manner and have a solution that includes the services of the three levels. Example of this, if you are using, for example, Dropbox or Google Drive, you are in fact accessing infrastructure. Dropbox assigns you with a specific set of storage of disk that you can use. And the storage, in fact, is distributed, okay? So different disks compose the offer that provides Dropbox. It also provides guarantees, for example, availability, which means that your data is replicated. And so, but anyway, you are accessing to this infrastructure, disk, hard disk. Okay. Now you are in order to avoid you going and deciding where to put the data, it provides you with a file system level. In fact, what you see when you access Dropbox, either in a mirror on your computer or on the browser, you have a file system, and then you create your files and organize your data, and transparently this data go through the different storage services, the different disks that you are allocated in order to store them. Okay. And then to avoid also having a not very friendly way of using your file system, you have an application, which is the one that you see on the browser or in your computer. In our computers, we even install a Dropbox app. And the Dropbox app is, in fact, a software as a service that helps us deal with the file system in a graphical manner. We are not using operating system commands in order to go through the files. And so this graphic interface that we use, and that allow us to organize our data, and then transparently the data goes through there. And if we need more data, more space, well, we can put our credit card, and then we enlarge the amount of data that we can store in Dropbox. So you see, so this is the kind of solution that we can have in the cloud, and there is a corresponding set of configurations that we can use in order to deal with our data science experiments, both the data and the pipelines. Questions until here? I'm going to, while you decide whether you have questions or not, I am going to ask you, while I explain some things, to go to this address and create an account. Please try to follow the process with me, because we will use this activity, the results of this activity, when we will go to the lab. This is just a motivational, practical activity to start touching a lot of what I've said with respect to the data. And then next time we will go through the experiments, one on top of what we will have done today on data. So while you create your Kaggle accounts, so for data science experiments, as I said, we need to deal with the data. And so today, there are environments that help us do, in a very friendly manner, our experiments. And they provide a service called Data Lab, which allow us to manage, in a curation perspective, the data sets that we can eventually use to run our experiments. Okay. And these are cloud services, okay, which means that they are flexible and etc. There are many vendors providing this kind of solution, Data Lab services. Some of them are, I have listed them here, but there are others. So Kaggle.com is the one that we are going to use in the first part of the hands-on. There is also Colab, which provides, in fact, relies on Google Drive, on our Google Drive spaces to deal with the data, and there are also solutions by Azure Notebooks by Microsoft. Okay, so in general, Data Lab service, again, it provides a layered architecture with many different subservices that allow us to manage our data collections that we will use for running experiments. First of all comes the question of storage. I have not a lot insisted, but I'm going to insist now. There is today people worried about who and where are our data. Okay, this is a very critical and important aspect that society in general and academia, of course, are addressing. So data labs, what allow you is to decide whether your data will rely on your own servers, your own disks. Let us consider that we have a company or that we are the NC3 and we want to manage and have full control on the data of the school, okay, in-house. So the data lab will allow us to do that and keep this control, or rely on a vendor, let's say Dropbox to say anything, or Google Drive or whatever, a cloud solution where we can put our data and then use them eventually. Okay, have access from the data lab service to this data, okay, this data collection. Or of course, we can have a hybrid solution. So the data lab allows this, will connect to the hardware support, if you want, where the data lies, and it will provide a file system, a distributed file system service that will allow us transparently to navigate through our data, okay? And these distributed file systems can have different forms, and we can use the ones provided by the lab, or if we have one that we like a lot, we can connect to that one. On the upper part of this architecture, of course, file systems are nice, but they are very simplified ways of dealing with the data. Sometimes we need more evolved data representations that can ease the operations that we can perform on top of the data. So they provide solutions, different storage, data management solutions, in order to help us deal with the data that are here a little bit of in a higher rawness degree. And it connects us also with data processing libraries of the ones that we like, Python, R, or others, in order to deal with our data. And there are other two important elements. I talked about curation in previous slides. Of course, you have the raw data, but the raw data doesn't mean anything unless you really control and know what the data contains. Otherwise, for other people, it doesn't represent anything. So that's one thing. And as I said, the data set is a living element, so new data come, etc. And so you can have a versioning strategy of the data, of the different status of the data collection a long time. You can also have policies in order to tag the data with metadata that can help people that are not the owners to understand the data. And also estimate the quality, the quantitative quality of the data, okay? And have a comprehensive representation of the data that are here raw. And so the data lab provides us with this type of services, okay? Why? Once we maintain all these data sets, then, well, the Kaggle solution that we are going to see in a minute has a spirit of sharing, okay? So you can share the data sets with the community. You can also share the type of experiments you have run with the community, such that when someone is willing to understand some problem, the person can look for data and previous experiments that have been done on the kind of question she or he wants to answer. And so do not start from scratch, but start from the experience of other people, and then design and run his or her experiments, okay? So this is, or we can keep them, of course, private and do not share them with the community, okay? So this is the spirit of this kind of vendors, particularly Kaggle and Azure. And but anyway, the general architecture of a data lab is the one that I have described now. Now we are going to move. I suppose I am going to assume that you already have created your account while I've been talking, and I'm going to move to Kaggle. Okay. When you connect to Kaggle, so kaggle.com, and I have an account, etc., you are going to land to this interface on the browser. And you are going, in the left side, you are going to have many services, okay? So the basic ones that I have described, but other services. Just for of course, you are going to have the data sets service where you are going to deal with the data in the way that I have described. But you can also have models, code, discussions. They run competitions, and some people some companies and other organizations provide data and provide problems. And so teams inscribe in these competitions, and there is a prize, a monetary prize. And so they provide you with a month or with some time in order to address the problem. And then if you win, well, you have this prize. So many universities, particularly in the States and in other regions of the world, here in Brazil, they are very active, or in Mexico, they run these competitions, and so they participate, and they have coaches, and in order to learn and acquire very good expertise on data science, okay? So these are other things, and there are courses, of course, etc. So I'm going to concentrate on the data lab aspect. So if you click on data sets, you will land here. You have in the general interface two buttons, so creating your own database, or having a look on previous databases that you have created. And here you have the data sets that have been shared by the world, okay? You can, this works as a search engine, so you can ask for topics, and so it provides you with data sets that claim having been used or containing data on the different tags, okay? So let's use this one. No, this one is horrible. Well, this one to show you. So a data set, well, this one is provided by, you have seen who, is defined as follows. So this is the curation spirit that I'm talking about. So you have the title of the data set. You can have a short description, and then you can have a real description of the content of the data set. You can tag it with topics that can be representative to its content. You know the frequency. So this is computed automatically by the system. As you as an owner of the data set, updates versions of the data, then the system knows that this data is updated quarterly. The owners can define a license of use, and its usability is 10. So it's very well described, tagged, etc. Okay. It has comments about the data, and then you have this. When you upload the data set, we will see, I hope, no, not today, maybe, but we'll see next time. So the data set, once you upload it, the system is capable of understanding the format. So it is a file, a CSV file named YouTubers DF, and it weighs 125 and something kbytes. Okay. Well, we are accessing to version 1, which is one CSV. It is one file, and the file. So here you have the structural description of the data set, which is automatically generated by the system when you upload this data set. So we know that the CSV has 9 columns. 4 of them are numerical. 3 of them are of type string. 1 is an URL and 1 is other. It doesn't know the type. Then you have well, the description, and here it generates automatically the quantitative description profile of the data set, which means that for every attribute, we are talking about CSV, so CSVs are tabular representations of data. For every attribute, it presents the distribution of the values of the attribute and the different values of each attribute, okay, the possible attributes. This is for numerical values. When you have non-numerical values, for example, a string, this has been provided by the owner, so they have a description of the attribute. The system has computed that there are 994 unique values, so different values, different strings, and it provides you with all these different values. Okay. Here, for example, it gives you the percentage of null values and the percentage of the different attributes values that it contains. So there is 60% of values saying música y baile, and other values 53%. Okay, and there is 31% of the content is null. Okay, so for each row you will have this. So this is the quantitative representation of the content. So when your colleague asks, okay, data exploration, which is the most costly phase of the data science pipeline, I said data exploration. As you can see, even if it can be costly, there are already tools providing a lot of help in order to reduce the burden of exploring the data. Of course, there are other more critical things where you still need to work. No? So this is the detailed representation. It has also a compact representation, and it has the statistics per column. So, of course, a person exploring the data would have to understand and have a look precisely on these conditions, but the person wouldn't have to program the statistical analysis of the data set in order to determine its characteristics. This is the type of service provided by the tool. Now, there are, I wanted to show you, I want to show you the licenses. Well, here, it also tells you that there has been a notebook that, well, I will not say what is a notebook now, but there has been an experiment that has been run on top of this data. Okay, so there are no discussions. And then with respect to the license, let's say, because I'm not having a wonderful connection, but so the owners have decided to acquire this type of license to the data set. And if you click, it provides you with the information about the conditions, the statements of the license to determine how to use the rights of using the data set. Now, if you are generating a data set, this means that if you want to be perfect and that have full control and very good practices on the way you manage your data, you would upload your data set and see what is generated automatically, particularly this, but then complete with metadata and descriptions that will allow someone be guided about the content of the data set. Okay, so today we won't have time because otherwise we will rush, and I think that we have to do this calmly. But the next time what we will do is we will create our own data set, the one sets that we will be using for our experiments, and we will technically see how does it work, and then we will see a second service provided by these kind of tools, which will allow us to design our experiments and then start using our data sets to run experiments on top of them, with a certain number of discussions that I will introduce with respect to this design exercise. So, do you have questions until now? So I'm going to stop sharing my screen. So today we have an overview of the main aspects behind, the epistemological aspects of data science and big data, which is datification with its ambition. Then we introduce the characteristics of big data and particularly the properties. The properties are those that you have to bear in mind and be able to master. Then we saw the two principles of using data with classic perspectives on factual data, and then the data science perspective. And then we have started to see how a concrete tool can let us deal with a data set, curate it, and eventually in an externalized manner, okay? With the help of a cloud provision of resources. And this is the summary of the two sessions. I thank you for your attention. I remind you that you can contact me if you have further questions. And for those that arrived at different moments, the new version of the slides will be online. I will also put the two videos of the two sessions that we have. If you missed something, and I'm looking forward to meeting you again next week. Thank you very much for your attention.
Thank you.
Bye-bye.